This is our first in a series of videos exploring rational expressions. The first thing we need to do is figure out what is a rational expression and how to simplify them. Then we can start doing some more evolved stuff like multiplying and dividing, adding, subtracting, and then solving rational equations. And eventually take all of that knowledge and put it together to graph rational functions. So before we do anything, we have to understand what a rational expression actually is. So I'm going to write an expression out here. This is problem number one. X plus 4 over x squared plus 4x plus 5. What makes this a rational expression is the fact that we have a variable in the denominator. We have a fraction where we definitely have a variable in the denominator. We could have one in the numerator as well, which is not a requirement, but sometimes that happens. But the key is that there's variables in the denominator. So what's going to happen is we're going to run into issues where we have what are called excluded values, some values that present a major problem for us. So one of those issues that we're going to have is that we can't divide by 0. That's outside the rules of mathematics. We simply can't do that. So in order to figure out how to simplify this, our general strategy is going to be look to factor. The first thing I want to do is see if I have any greatest common factors. Anything in the numerator where I can just take something out, or anything in the denominator where I can take something out. Now I'm not seeing that in this example. So my next step is to look do our traditional factoring. So in the numerator, I really can't do anything with that. I'm going to have it as x plus 4. In the denominator, I can factor x squared plus 4x plus 5, x plus 4, and x plus 1. You might notice that in the numerator and denominator, we have exactly the same factor, x plus 4. And in the end, those will eventually cancel out. But what I want to do first, before I start canceling anything, is look for problems in the denominator. The problem that we have is that we can never divide by 0. So I actually have two factors that could potentially pose a problem for us. That for particular values of x, they're going to return a 0 in the denominator, which is just really, really bad news. So what I'm going to do is take each of these factors, x plus 4, and I'm going to set it equal to 0. And I'm going to do the same with x plus 1 and set that equal to 0. Then I want to find the value of x that makes that equation 0. We've got negative 4, and we've got negative 1. Now, what this tells me is that my function is going to have two excluded values. My excluded values, x cannot equal negative 4, and x cannot equal negative 1, because both of those values return a 0 in the denominator. But we've got to classify them as well, because they're going to have different implications on the graph. So when I look at these two values, noticing that x plus 4 canceled out, that's what's called point discontinuity, or another way to think of it is called removable discontinuity, because we can remove it and see how the function is actually supposed to act. So that will simplify down to this. So this right here, x doesn't equal negative 4, indicates a point discontinuity, a hole in the graph. And we'll see that more later on in future videos. The one that doesn't cancel, or if there's one that doesn't cancel, any factor that doesn't cancel, would indicate a vertical asymptote. And the way we're going to classify that is an infinite discontinuity. So if I gave a little rough sketch of the graph, so we are going to have a whole bunch of stuff going on, but at negative 1, we have an infinite discontinuity. I'm going to have a vertical line. That's my vertical asymptote. At 0, and I'll show you later how we're going to calculate this, but at y equals 0, we're going to have a horizontal asymptote. And then we've got a point discontinuity at negative 4. And so what I'm going to do is I'm going to take a particular value, let's say 0, and I'm just going to plug that in so I can get a rough shape of what the graph looks like. So that would be at 1. So it looks like my graph, this is pretty typical of a rational function. It'll look something like this. But at negative 4, and I'm estimating here because I don't have any scale on the axes, but at negative 4, I'm going to have a hole in that graph. And so my graph will look something like that. And that's typically what a rational function is going to look like. So again, if the factor does cancel, it's a point discontinuity. If it doesn't cancel, then it's infinite discontinuity. Let's grab another example. On this one, we've got x squared plus 6x plus 9, and we are dividing that by x squared minus 9. So once again, I'm looking for take anything out of the numerator, and I don't see any common factors between all three terms. Do the same in the denominator. I'm not seeing that either. So I don't think there's much I can do there. But my next step is to take this expression and factor it. X squared plus 6x plus 9 will turn into x plus 3 times x plus 3. And the denominator, x squared minus 9, becomes x plus 3 and x minus 3. Once again, I've got a problem because if I've got variables in the denominator, I have potential excluded values. I'm going to find out what those are. And so when I solve that, this one is going to tell me that x can't equal negative 3, because that factor will turn into 0. And over here, x cannot equal positive 3. So again, we're looking to classify them. X plus 3 is a duplicate factor on the top and the bottom, so I'm going to cancel out just one of them. And notice when I found the excluded values, I wasn't really concerned at all with the numerator. Okay, if the numerator is equal to 0, we can take 0 divided by something, but we can't take a number and divide it into 0 pieces. So again, this x plus 3 is a factor that canceled out, so that would indicate a point discontinuity. And x equals 3 would indicate, I could spell it correctly here, geez, an infinite discontinuity. And so again, there'll be a vertical asymptote at x equals 3. And a vertical asymptote, again, is a line that the graph can never define at that particular value. All right, one more. Let's make this one a little bit more complicated. So this third one here, we've got 2x squared plus 9x minus 18 over 4x squared minus 6x. Looking in the numerator, I don't have a greatest common factor. There's nothing I can take out of both of those, so I can't really do much with that. In the denominator, though, I do appear to have a greatest common factor. 4x squared and a 6x. I think I can take a 2x out. So it becomes this. Two x times 2x minus 3. So something to keep in mind, if you take out a greatest common factor, that doesn't necessarily mean you're done factoring. In some cases, when we take out a GCF, that's what I'm going to call the greatest common factor, the polynomial that's left, we can still factor it. In this case, we couldn't. However, we can factor the numerator. And so when I've got 2x squared plus 9x minus 18, that's going to give me a 2x and an x. And I believe I'll have a plus 6 and a minus 3. So at that point, I can take each of my factors in the denominator. And this is where it gets a little bit goofy because we took out a GCF, a greatest common factor. That 2x is a factor that we have to solve. 2x equals 0. 2x minus 3 is a factor that we need to solve. So I've got x equals 0, or can't equal 0, I should say. And solving that, I'm going to add 3 to both sides and divide by 2, and I get 3 over 2. So if I'm looking to simplify this, I'm going to cancel out that 2x minus 3 because that factor cancels. That means that excluded value would be a point discontinuity, or again, a hole in the graph. So it's an empty space. It wants to achieve that value, but it doesn't actually do so. And the factor here that doesn't cancel would indicate infinite discontinuity and a vertical asymptote. Key point of this whole thing, though, is when you're looking for excluded values, it's extremely important that you find the excluded values before you start canceling. Otherwise, you're going to lose out on all those point discontinuities, which are important for the implications of graphs.